Let's talk about conservation of energy. Conservation of energy is a fundamental principle of physics. However, you can see it using the work kinetic energy theorem. You may recall that the work kinetic energy theorem says that the net work done is equal to the change in kinetic energy, where we understand the net work to be done on a system and the change in kinetic energy to be the change in kinetic energy of a system. Remember that the net work done is the net work done by all the forces acting on the objects in your system, whether they are internal forces or external forces, whatever kinds of forces they are. So we can split our net work term into work done by conservative forces and work done by non-conservative forces. Now remember, the work done by conservative forces is equal to minus the change in potential energy. Therefore, we can plug this expression in to our equation up here for the work done by conservative forces to get as follows. Now we can move the potential energy term over to the other side of the equation, and we see then that the work done by non-conservative forces is equal to the change in kinetic energy of the system plus the change in potential energy of the system. Well, what happens if there's no work done by non-conservative forces? Well, if there's no work done by non-conservative forces, or more specifically, no net work done by non-conservative forces, then work done by non-conservative forces is equal to 0, resulting in this equation right here, which is known as conservation of energy. Why do we say it is conserved? Well, the changes in kinetic energy of the objects in our system and the changes in potential energy for all the objects in our system must be equal to 0. So there is no net change in energy. You can have kinetic energy changing into potential energy or vice versa, but no energy is being added to our system, no energy is leaving our system. And so we say energy is conserved. More specifically, we say mechanical energy is conserved. The change in kinetic energy plus the change in potential energy is called the mechanical energy. Remember also that this work by non-conservative forces, they could be external forces or they could be internal forces. We need the net work done by them, wherever they are, to be 0 for energy to be conserved. Don't forget also that this equation is deceptively simple. This is standing for the sum of all the kinetic energies of all the particles in your system and the sum of all the potential energies for all the particles in your system. And likewise, up here, for the work energy theorem that we have up here, the net work done by non-conservative forces means we add up all the work done by the non-conservative forces, and we need them to equal 0 for energy to be conserved. So just remember, it's total change in kinetic energy plus total change in potential energy, and total work done by non-conservative forces needs to be 0 for mechanical energy to be conserved. Now, as I have alluded in talking about conservation of energy, to use conservation of energy, we need to think in terms of systems. So how shall we approach conservation of energy when thinking about systems? Well, to help illustrate things, I've drawn my favorite scenario of a rock falling down to the earth under the influence of gravity. And of course, the rock exerts a gravitational force back up on the earth. And we have two systems we can define here, either the rock by itself or the rock and the earth. So let's think about systems. So firstly, you can think of potential energy as the energy of conservative force pair interactions. So here I have conservative forces, and they are an action-reaction pair of forces. And we can think of potential energy as the energy of these conservative force pair interactions. Next, we can think of potential energy as being internal to systems. Why? Because potential energy is the energy of conservative force pair interactions. So that means potential energy arises as a result of interactions between two objects. So that being the case, it makes most sense to include both objects in my system. So that way, when I talk about potential energy of my system, both of the objects that create it are in my system. And so potential energy really makes most sense when thinking of it as being something inside a system. That being the case, the conservative forces that create that potential energy must be internal to the system. So potential energy is internal to the system, and therefore conservative forces must be internal to the system also. in order to define and understand a potential energy. Now, what I just said is true, and we'll hold that it's true for the rest of the class, but you should know that if you get more advanced, it is possible to define an external potential energy and have the rock inside the system and the Earth be outside your system, and then your rock has a potential energy in coordination with an object that's outside the system. But this can get kind of tricky to understand and a bit tricky to deal with unless it's a situation like this, where one of the objects, which we understand as the source of the potential energy, is not moving. So, namely the Earth, it doesn't really move. And then you can kind of think of an external potential energy as a background field. We call it a static field in this case because it's not changing with time. But you don't have to worry about that. Just be aware it is possible to define an external potential energy, but that's a more advanced topic. For us, we will always think of potential energy as being internal to a system. As already noted earlier in our discussion of conservation of energy, this work non-conservative term is the work done by all the non-conservative forces, whether they are internal to your system or external to your system. So it's the work done by all the non-conservative forces on the objects in your system. All of this work needs to add to zero in order for energy to be conserved. As a note, then, when defining your system, one useful thing you can do is leave all the non-conservative forces out of your system. So that way all the non-conservative forces are external to your system. And then all the non-conservative forces will then be doing external work on your system. This then tells us how we should think about systems of energy conservation. What we want to do is we want to create a system where all the conservative force pairs are inside the system. And optionally, we can leave all the non-conservative forces out of the system so that they are external forces. So, looking back at this example again, if I choose system 1 of the rock alone, then the gravitational forces are outside my system. They are doing work on the system to change the kinetic energy. Energy is not conserved in this system. If I instead define a weird system where I have the rock all by itself and the Earth all by itself, leaving the conservative force pair interaction outside the system, then those are still external forces, and they're changing the kinetic energy of the rock. They're not really doing anything to the Earth because the Earth is too big to move meaningfully, and so energy is not conserved in this system either. If instead I include the rock and the Earth along with their force pair interaction all within one system, I now get energy conservation. I have put my conservative forces inside my system. They are internal forces. There are no non-conservative forces acting, whether inside or outside the system. And so the work done by non-conservative forces is zero. And so change of kinetic energy plus change of potential energy of the objects in the system must equal zero. And again, change of potential energy is a system property. It is the energy of a force pair interaction. It is not the energy of any one particular object, whereas kinetic energy is the energy of particular objects. So I add up all the kinetic energy of my rock and of the Earth, and I add up the potential energy of this force pair interaction, and the changes in those must be equal to zero in this system as the system moves from state A to state B. So there is your fundamental principle. Draw your system so all the conservative force pairs are internal forces and leave non-conservative forces out of your system, or at least leave all non-conservative forces that do net work, net non-zero work, out of your system.